Matei Zaharia is the original creator of Apache Spark and a co-founder of Databricks, which provides data science powered by Spark. Matei, welcome to Software Engineering Daily.
Thanks, Jeff.
What is Spark?
So Spark is a parallel computing engine that runs on clusters of many machines and can be used for data processing.
And what was the motivation behind creating Spark?
Basically, we wanted to make it easier to process large volumes of data, which are very common both in a lot of commercial applications, but also increasingly in research. So at the beginning, Google really pioneered new programming models for large clusters of machines through MapReduce. But as more people started using this technology, and especially people who weren't software engineers necessarily, or who had other skill sets, you wanted to make it a lot easier to work with these kind of data sets.
How much faster is a Spark job than a Hadoop job?
Spark can actually run quite a bit faster than traditional Hadoop MapReduce for a few reasons. One is the ability to do a lot of the computation in memory, and the other one is that the engine understands more general communication patterns and patterns of basically dependencies between tasks in a job. So we've seen on disk, with just data that's on disk, we've seen it go as much as 10 times faster in some applications, just because it understands the structure of the job better. And if you also use memory and keep parts of your data can fit in memory, it can be 100 times faster as well. It depends, of course, on the application.
So as I understand, with Hadoop MapReduce, every operation is actually 3 operations. You got map, shuffle, and reduce. And so if you have n higher level operations in Hadoop, you actually have to do 3n operations. But with streaming frameworks like Spark, you have a finer degree of granularity, and you can simply chain operations together along a directed acyclic graph. Is this correct?
Yeah, that's exactly right. Yeah, so basically in MapReduce, many applications need to take multiple MapReduce steps, and it's very expensive to pass data between these steps, because you have to basically write it out to a distributed file system and replicate it across 3 machines, and then later you load it all back in. Spark understands the entire sequence of steps and can just push data through between them.
Spark uses in-memory primitives rather than Hadoop's 2-stage, disk-based MapReduce paradigm. Why wasn't Hadoop created with in-memory processing power?
Mm-hmm. Yeah, I think that's a good question. I think there were 2 reasons for this. So first, when Hadoop and MapReduce came out, memory sizes per machine and per dollar cost were a lot smaller. So the cost of memory has actually continued to fall very quickly with Moore's law, and suddenly now a lot more data sets can reasonably fit in memory than they did back then. So that's one of the reasons. Is just the hardware back then wasn't good enough and cheap enough to be able to do this. But the second reason is I think the applications back then were just simpler, and they were these long batch processing applications where in many cases you didn't need to do too many MapReduce steps, and the overhead of it wasn't such a huge deal, because you just let it to run overnight, and in the morning you got back an answer, and that's all you wanted. And again, people move towards applications that they want to be much more interactive. Like there's a person sitting there asking questions and they want to get an answer back, a few seconds later, or there's real-time data coming in and you want to act on it right away.
Does Spark completely replace Hadoop MapReduce, or are there still pockets of task where you would say Hadoop and MapReduce is a better or more appropriate tool?
Yeah, so for MapReduce in particular, Spark is meant to be a generalization of MapReduce. So you can still do all the things you could do with MapReduce in Spark, but you can also do other things, other types of applications that are harder to express efficiently with MapReduce. So in that way, it's meant to be a superset of MapReduce. The Hadoop stack also contains a lot of other components, though, and these are things that Spark can work with and can integrate with the same way MapReduce did. So, for example, Hadoop also comes with a distributed file system, HDFS, and you can't replace that with Spark. Spark, doesn't have a file system. It's only a computing engine, but you can connect Spark to HDFS and use the data that's in there.
Eli Collins, the chief technologist at Cloudera, came on this show and said that batch and streaming are on opposite ends of a gradient of processing speed. What are the parameters that can be tuned to explore the different sides of this gradient?
This is in Spark, right? You're asking. So basically, in Spark, you can control. So you can run these jobs that that process some data, and depending on how often you run these jobs, you can get either something where you run, you have a large data set and you run a single job, a single set of operations that processes the whole data at once, and that's a batch job. Or you can run smaller ones continuously as data comes in, and each time new data comes in, you run a small job and then you update the state in memory that's tracking whatever your application wanted to track, and that's how you can have a streaming application that keeps updating state as new data arrives. So basically, you can use Spark in both ways. The engine supports running really small, low latency jobs. It also supports running large jobs that go for many hours and where it has to deal with things failing and restarting in the middle of the job and so on. So it's kind of this job size that's the main parameter.
Are Spark jobs typically run on datasets that are smaller than Hadoop datasets?
I think that's pretty hard to tell, actually.
So those are totally orthogonal things.
Yeah, I think that's hard. Exactly. So there are companies and organizations that basically use only Spark, that don't use MapReduce at all, even for the large scale batch processing. And we see this especially in ones that just recently started building, say, big data pipelines or products, and for them it's easier to just grab and do Spark for everything. There are also companies that have MapReduce already for some jobs, and then they bring in Spark mostly for new applications, which might be on smaller data sets where they need more interactivity. But the largest Spark jobs are, as large as any Hadoop job I'm aware of. So the largest cluster we've seen is 8,000 nodes running, kind of just as a single cluster running, single jobs. And the largest jobs we've seen are jobs on multiple petabytes of data that could run for weeks. So Baidu, actually, I forgot if it was Baidu or Alibaba, but one of these Chinese web companies ran Spark to do basically to transform all the images into features for machine learning algorithm, and they processed 1+ petabytes of data over the course of a week, just crunching through it to do this.
Yeah, I heard the podcast where you mentioned that, I think an RCE Podcast, I think you said it was Alibaba, and you said there was
I think that was it, yeah.
Yeah, you said there was a petabyte of image processing, and it took 3 days. Do you have any estimations on the financial cost of that kind of processing?
It can be fairly expensive. So I think that was like I forget how many nodes in there that were in that cluster, but when you get to like 1,000 nodes, just keeping them running, is thousands of dollars, per day. So it's definitely expensive. In these companies, generally it's worth it because they do many different applications using the same data, it's basically there are many parts of the business that can use this. So they just bring all the data together. Yeah.
And how efficient? I mean, maybe you can't really speak to this, but how efficient do you think the processing queries that they were running to do that image processing were? Could they have saved a lot of cost just by improving the way that they were processing those images?
Mm-hmm. Yeah, it's I don't know too much about this specific application, but in general it depends a lot on the application. So basically, you need to do so for this particular one. Image processing is actually very CPU intensive, and there are really good libraries out there that use modern CPUs efficiently, that use multiple cores or vectorization, SSE, things like that. So you really need to use one of those libraries in your Spark job to get the best performance. Otherwise, if you just like write it, kind of naively by hand, you can throw lots of computers at it, but the efficiency per computer will not be very high. So I think my guess for this is that, there are so many of these libraries that probably they are using one of these, but I don't know the specifics. In other applications, especially if there aren't really great standard libraries for what you want to do, there's a trade-off between, do you spend a lot of time engineering it and like building a super efficient library, which costs you, like human time, or do you write something quickly and then you can run it on a large data set and like see how well it really does. So in many cases, like people actually, the people time is more valuable, especially if this is like a one-off thing that they're not sure they want to do again. So they focus on getting something built quickly, and then if it works well and there's like, okay, we want to run this again every day, then they focus on optimizing it.
How painful is the minimum viable migration? If a company has just a batch framework and they want to implement some sort of streaming into their workflow, how painful is the minimum viable migration in terms of cost and developer time?
Mm-hmm. Yeah. So okay. So I think that depends a little bit on whether the batch job they have is written in Spark or is written in MapReduce or some other framework. So if it's written in Spark, the API, the programming interface for Spark streaming, is very similar to the interface for the batch jobs. And you can often reuse a lot of the functions you have in your batch jobs and apply them to a stream instead. And there's very similar operators and so on. So you do need to learn, how the streaming model, how it works, what's slightly different about it. But you can reuse a lot of the same code. And in fact, you can even tell it, like, for instance, like split the stream into, say, 10-minute windows or something, and then run my batch job on each window. That's very easy to set up. If they're coming from a different framework, then they need to actually basically write their computation in Spark. And it is the good news there is it's possible to use, for example, all of the input formats for Hadoop, which are all of the interfaces for Hadoop to access stored data. So you can still use the same data and read it and see it in the same form you got it there. And with a bit of work, it's possible to use a lot of the map and reduce functions you'd write as well. But that, I think, takes more engineering because you have to learn all of Spark. And we've definitely seen people do that.
Has that simplified migration process, is that a competitive differentiator for Spark versus Storm or Samza?
Yeah, I think so. I think especially, for people who do, say you develop your analysis as a batch job and then you want to create a streaming job, or say that even you do the analysis interactively. So like, for instance, from the Spark's interactive shell, like the Python interpreter or something like that. And then you can type in some code in there and you can then take that code and move it into a job that you run periodically. So that's a unique thing about it. And it's not just the migration, but it's also maintaining the code after, like making sure you get the same answer from your batch job and your streaming job, and fixing bugs in both of them and so on. Often it gets pretty hard to maintain two separate systems and keep them in sync when they're slightly different.
So let's talk a little bit more about the differentiators between Spark and Storm and Samza, or even Apache Flink, if you want to go there. What do you think would be the most interesting comparator to discuss with Spark?
Yeah. So I think there's like two main differences to look at. So one is in terms of being a unified framework to do both, batch processing, interactive processing, and streaming. Spark is the only one of these systems that can actually do all of these things. In some of these engines, you can use the same engine, say for batch and streaming, but actually you can't combine the two in a job, or like it's a different API. But in Spark, you can actually combine all of them in a single application. So, for example, some things you can do in Spark that are really hard in the others are you can take the code for your batch job and run, basically almost the same code on a stream and get streaming results. Or you can run a streaming application, update some state, keep track of some state in memory, like what are users doing on your website, and then start running interactive queries on that state. And the same in memory data. Just connect like a JDBC server and start running queries. So that's unique to Spark because the engine understands all these and they're all designed to interoperate. They follow kind of the same API. And the second difference comes in on the streaming side. So if you look at the streaming side, the model for stream processing in Spark is slightly different from traditional stream processing in some interesting ways. So traditional stream processing engines have these continuous operators where you push data through, and the operators are long-lived and they have state associated with them, and you keep pushing tuples through this like fixed graph of operators, and they update some state as they go along. That model is like pretty simple to understand, but it's actually pretty hard to do operationally because fault tolerance becomes really difficult when one of these goes down. Everything downstream and upstream is affected, and you need a pretty complicated method to recover. Things like dynamic planning, like scaling, increasing the number of nodes in your cluster or things like that become very difficult as well because it's a fixed graph. And also throwing in new queries or these interactive queries, as I mentioned, is not really possible because you decided on this graph of operators in advance.
The company that sorry, go ahead.
So that's kind of the traditional model, and the Spark model for doing streaming is actually different. It's this sequence of very short jobs, MapReduce like jobs that share data and memory between them. So it means we can adapt to changing workload patterns much more easily because if we see there's a lot more data, you can just launch a job with more tasks and dynamically change the level of parallelism and so on. It means it's also easy to throw in other jobs that do interactive queries or like some ad hoc queries that you hadn't anticipated before, and you get actually much stronger fault recovery guarantees because it's the same like deterministic fault recovery that you get with batch jobs.
The company that you started, Databricks, is building a data science platform based on a commercialization of Spark. Mm-hmm. Describe the product offering of Databricks?
Yeah, definitely. So the product offering is a hosted software as a service platform that makes it very easy to run Spark and in general to build a big data infrastructure as a team. So the thing it provides cluster management. It's very easy to launch Spark clusters. Have multiple clusters for different users, scale them up and down elastically, and so on. And then it provides this interactive collaborative workspace on top where multiple team members can connect to one of the Spark clusters, run queries, share like the outputs they produced, and share visualization as well. So as this interactive notebook like environment with these features built on top of it.
So in that podcast that I mentioned earlier, the RCE podcast, you mentioned that one of the unexpected uses of Spark that you saw was people who were writing Spark backends with web app frontends. And so, but it sounds like what Databricks is it's a company that facilitates that. Was that basically the inspiration? Like you were like, whoa, we're surprised by how many people are doing this. Let's just build a company around it.
That was part of it. Yeah, I think early on when we started the project, we just didn't. we hadn't thought too much about this use case, but it makes a lot of sense. Basically, people people create like a domain-specific application. Like, here's an application for understanding, video viewers, or for understanding like ad clicks on a social network or something like that. And when that application needs to run new queries, it talks to a Spark cluster, and it actually can process a lot of data interactively. So we wanted to enable things like that. It's not the only thing we do, though. We also just wanted to make it very easy to just run Spark. So you can just build a job and deploy it, and not have to worry about managing a cluster or configuring it, tuning it for the hardware, and so on. But we were definitely excited about this.
How does Databricks integrate with Cloudera?
With Cloudera, so the Databricks, the product isn't. Are you asking about the product or about the company?
I'm just wondering, like, if I'm building a platform where I have some of my data on the Cloudera platform and some of my data on the Databricks platform, is there any point of integration, or are they kind of mutually exclusive?
Oh yeah, no, definitely there is. So, and actually, we see people doing that. So if you run a Cloudera cluster in Amazon EC2, which is where we are right now, you can read data from it into Databricks. So you can easily connect to any data source that Spark understands, including HDFS clusters and HBase and all the other storage engines in there. And we also have people connecting it to on-premise clusters and pulling out the data that they want to work with interactively into Databricks. So Databricks itself actually, doesn't lock you into a specific form of storage. It's meant to work with like any common form of storage that's available in the cloud. So you can just bring in the data from all of those and combine it.
Yeah, I think that's a great policy because one of the I've been doing these interviews with these big data companies, and it's interesting because we've developed this kind of ecosystem where you have these different like big data service providers, and it's really nice that it seems to be like they're all copacetic, right? They all integrate with each other well in this like nice collaborative way, and it's not like this animosity land grab type of situation. Does that kind of surprise you, like just from an industry type of perspective? It seems sort of unprecedented.
Yeah, well, it's not like completely true, but there is a lot of interoperability. I think all the vendors of these platforms would prefer if you remain more locked into their platform, and some of that happens because they have, for instance, like they have their own, say, storage formats for data, like a file format or something like that, and they each have kind of their preferred one. But because they're all shipping this open source software, and there are very well-defined interfaces to access this stuff, it's pretty easy to use anyone's software to access sort of anyone else's data. And I think that's really great for users of the software, and it basically leads the vendors to they're not they won't get business by kind of locking you in, but they'll get it by actually having a better product with something that you really want to buy. So I think it comes a lot from the open source aspect of it. I think this never happened with, say, commercial databases, because like the whole purpose of a database is like it's this complete enclosed system that's like totally it only works with that same vendor, more or less.
If you have a current, like a heterogeneous managed big data stack, you've got Confluent for Kafka, Databricks for some Spark, Cloudera for some Hadoop. What is the current end user experience for somebody that is managing all these different systems at a company, and how do you project that to change into the future?
Yeah, so that's a good question. Yeah, so managing these now is actually fairly complex. It's even actually if you have even just a single vendor, but if you have a Hadoop distribution, it comes with many components in it. Like there's one component for stream processing, one for batch. You have Hives for metadata, stuff like that. So it is pretty complex, and I hope that this stuff gets simpler. But now, basically, you need to learn how to manage each of them. So at least what we're doing at Databricks, but I think this will be a general trend, is we kind of said from the beginning we're going to focus on cloud and on software as a service, and that allows us to do a lot more of the management kind of for you. So with basically with all these cloud services, not just ours, but many of the others, there's someone else who has ops people who are keeping the system up and running all the time. So you just focus on using it and figuring out whatever application you want to build. So I do think this will be the main way to simplify things, is if you can offload the management of it to one of these cloud vendors. And then the question is how these are going to integrate with each other, and that's a really good question. I think there is, just because people ask for it, there is a lot of integration happening, but that remains to be seen.
Do the vendors have any trouble hiring enough ops guys to work for clients?
Well, the on-premise vendors, like the Hadoop vendors, really don't they don't actually provide ops for clients, and they don't basically want to be in that business, because it's a business that's basically it's very easy to compete with in that business, so it's very hard to differentiate yourself. And the way they've traditionally worked is they work with each customer's own IT organization, and they train them to do this kind of management. But that's pretty tough, because you have to learn all this stuff that changes. For the software as a service companies, like if you look at Amazon or at Databricks or Google, any of these kinds of companies, the ratio of ops people to number of customers and so on is much smaller, and it's much more efficient because they have a lot of built-in software that makes it easy to manage multiple of these. So they get economies of scale basically from that. So
how does the Spark open source ecosystem compare to Hadoop's ecosystem?
Yeah, so in many cases they actually overlap. A lot of software that works well with Hadoop can also work well with Spark or has plugins. So,
I meant more in terms. I meant more in terms of the way that the developers interact with the open source.
I see.
Yeah.
Yeah. Okay. So there's actually, that's a good question. So there are actually some things that are different in Spark, and some of them are because we wanted to do things differently, basically based on what we thought had worked well in Hadoop and what didn't. So one of the main things that's different is Spark as a project includes this general computing engine, but it also includes a ton of the libraries built on top, like SQL or machine learning or stream processing, that in Hadoop these were completely separate software projects. And the benefit of this is, it means that all the libraries work together in a nicer way. There's opportunity to integrate them or to make a change that touches many libraries at once and makes them consistent. And they also get released on the same schedule. So you download one software artifact and it has everything. No one worries about having a distribution of Spark. The only reason you need distributions of Hadoop is because there are these different projects that release stuff on their own different timelines, and someone needs to actually bring together a consistent set of them and make sure they work together, kind of like Linux packages, the same reason you have Linux distributions. So this is one thing that I think makes it simpler, and it does make the project bigger, and there's a bit more management you have to do of it, but I think we made it work pretty well, and we get a lot of the benefits of this model. The second thing that Spark did that I think, this also happened in Hadoop, but I think we're spending a bit more effort on it, is we also have a very easy, very standard interfaces to plug in new data sources, new machine learning algorithms, for example, and new sort of third-party packages that make it easy to bring in stuff from outside. Any stuff that we don't want to include in the standard library, there's a pretty clear way to add it in there, and so everyone who wants to write one can see how that will plug in. And this is similar to like the way you have in R, for example. You can easily install any package, and there are tons of people writing packages that are very easy to use. Yeah.
Docker has been in the news a lot lately because it adds a layer of usability over Linux containers. What are the synergies between Spark and containerization technology like the Linux containers that Docker uses?
Yeah, good question. Yeah, so we do see Spark deployed, increasingly often on, on container-based platforms. So we see people running it on Docker, or more generally on some of these frameworks that do, distributed systems on top of Docker, like Mesos and Kubernetes and so on. So I think that's the main way it's being used. It's pretty nice. It's also pretty nice for local development. So a lot of people use Docker to package, like, say, Spark and like a bunch of libraries they depend on for local development.
How do container platforms change the cost structure of a Spark platform?
I think I think basically it's probably not an enormous difference, because usually Spark clusters are designed to have multiple applications, multiple users already, and they can already share resources between them through some kind of cluster manager. But what they offer is you can run Spark on the same cluster that you run a very different set of workloads on. Like, say, you also run web applications, or you run like your build system, your build server, like Jenkins or something like that, and you can move machines. Like when you have machines that are idle, that are not doing Spark stuff, you can assign them to other things. So I think the main benefit of these platforms is how many different types of things can run on top of them and can now share resources because of that.
Much of the recent developments within Spark involve work on making rich standard libraries, and these libraries include things like k-means clustering, sliding windows, machine learning. Talk more about the development of standard libraries.
Sure. Yeah. So basically, we decided pretty early on in the project that we wanted to have very rich standard library that's built into it, so that all these things are consistent with each other. Because as I was mentioning before, when we looked at the model in Hadoop, like, people were building really great libraries, but they were building them separately, releasing them on their own cycles. Some of them weren't compatible with each other, or were like hard to install alongside each other, and that made it very hard for users to quickly pick them up. So we started, we added streaming, I think, probably like about 3 years ago, and then machine learning and graph about 2 years ago, and we've been continuing to add stuff since then. And the main focus is to have a really good API that's consistent across all the libraries, and to add in things that we are sure that we want to support long term. So, like, we don't want to ever add something into the library and then decide, like, oh, there's no one who can maintain this, or no one's really using this, and we have to remove it. So we've basically, the one thing we focused on with them is stability. So we in some cases we err on the side of caution. Like, we only put in algorithms that are very commonly used and that we're pretty sure we can continue to have later. But I think overall the models worked well, and we've seen a lot of people start to use these. And if there are new things they want to do that aren't in the libraries, it's also easy for them to release something else alongside it. And the libraries provide standard template for like what the API should be like and how to plug it in.
You also mentioned that Spark's interface with R was a highly requested feature. Why is R so popular for use with Spark?
Yeah, R is just in general, it's probably the most widely used language for statistics and data science. So it's taught in a lot of schools. Most courses on statistics, will teach you like a little bit of R if they have some computing element to them, and so a lot of people know it, and it has just an amazing ecosystem of packages built in that you can just download and use. So it was very natural to try to use that. And then R is also well known for it runs well on a single machine, but it can't really use multiple machines or even multiple cores on the same machine very easily. So there was a lot of room to take the stuff people are familiar with and run it faster at larger scale. So that's why we ended up working on it. The support for it is still early on, but we see people beginning to use it, and there are also a lot of people contributing patches to make the R support better and to add more and more functionality in it. So I'm excited, to see how that continues.
These people who are using R, are they mostly just like using R as a raw interface to whatever data is available to them with Spark, or are these the same people that are building web front ends, and the web front end communicates with R and the R communicates with Spark?
They'd usually be different from those. The web front ends are more like the complete applications, like written in, say, Java or Python or something like that. The R ones are more for exploratory, like data analysis. So you have some question you want to ask, and you want to build a meta model to predict fraud or something like that, and you try many different approaches, and R is very good at prototyping those. So it's more data science than like end-to-end applications.
What are some other features that are highly requested in Spark today?
Yeah, it's quite a bit of stuff that people want to do. I think some of the ones I've seen, most commonly asked for are geospatial data, so libraries for working with geospatial data, and same thing for time series. So these are like a couple of things that aren't in the library already, but that would make a lot of sense to include. And then there's always, there's always new things we can do to add in more functions or to improve usability or performance or things like that. So there's quite a few of these, that are coming out, and we are working on them. Yeah.
What assumptions about the future did you make when you created Spark?
Yeah, I think so basically, I don't think there was anything too crazy, but there were a couple of things that were interesting. So like one thing, we definitely assumed that the users who want to work with with big data sets, there'll be more and more users, and they'll want to do it more and more quickly. So they'll want to do a lot of stuff interactively or in an exploratory way, and less of like, let's spend 3 months to build this application and then it's going to be in production for like a year. So people what this means is that people will want higher level programming interfaces that do a lot more stuff for them under the covers. So that's why we focused on high level APIs and on languages like Python early on, and then R now, that are accessible not just to like hardcore software engineers, but also data scientists or analysts whose main job isn't to write software. It's they have like some domain knowledge in a specific field. So this was one of them. And then we also did, assume that in terms of hardware, there'll be a move towards, faster random access style memory. And it's not just RAM itself, which is, what people talk about a lot with Spark, but also Flash and some of the new types of non-volatile memory announced, like the 3D X point from Intel and Micron, are great technologies for something like Spark, where a lot of your data can be in a in something that's much faster to access than disk, and then you have to manage that space and figure out what needs to be in there, how do I move it across between machines, and so on.
So I find it interesting that Databricks has a concerted focus on the data science area, and I think it's actually really smart, because data science is obviously a field that's exploding, and I'm curious, what are your thoughts on like how big the field of data scientists gets in the future? Because right now it seems like there's there's a lot of people who maybe are underemployed, or they don't exactly have the technical skills to get a data science position, but it's like, they're qualified, technical, intelligent people, but their jobs are kind of like disappearing. And so these are like people that are well suited to learn data science in the future. So anyway, what are your thoughts on the data science space?
Yeah, definitely. So yeah, I think most people who look at this will say, yeah, data science is a very rapidly growing sort of job title and job area, and we do see a lot of people starting, and we also see a lot of companies beginning sort of data efforts where they would need data scientists. One of the things to keep in mind also is that it's not like a completely new thing. In some sense, a lot of the people that previously were considered, say, analysts or like data analysts, this kind of position, are do the same kind of stuff we'd call a data scientist now. So in some way, it's also just a new label for something that people were already doing. But I think the reason it will increase is because more companies can easily store data now, and data about their business, and it's a competitive advantage to use it for something. So increasingly, you have to do that. The one reason we want to focus on them is in addition to engineers, which are obviously also very important users of Spark, is because the data scientists need basically they need easier to use tools to work, even with stuff on a single machine, but definitely with anything distributed across a cluster. They will not have the time and patience to actually spend a lot of time to build something complicated, because they often have to answer a question within a few days and move on to like the next question or the next project that they're doing. So that's why we want to make sure that what we're doing is good for them. And the cloud model from Databricks works really well for them, because they don't need to install software, manage it, configure it, all the stuff that's very time consuming, and it's not like what they primarily are experts at in their job. So it's very complementary that way.
Do you think that the massive use of Excel is a sign of pent-up consumer demand?
Yeah, I think Excel is used for different stuff. So some of the things you do in Excel, it would not make sense to use Spark for them. It's just for basically it's like simpler stuff and stuff fundamentally on smaller data sets that actually fit in your one Excel spreadsheet. But I think the use of R and Python and software like that is actually does show this. So I think the people using that could easily benefit from something like that that's faster, for example, even on a single machine, like something that actually uses multi-cores and can deal with data that's bigger than the memory of the machine and stuff like that. So I think those are the most interesting ones.
Do you have any examples for how Spark is being used in consumer domains like drones or virtual reality?
In consumer domain. So I think the best examples I've seen there have been like these kind of fitness tracking applications or wearables. That's kind of the most common one I've seen. So we've worked with a few companies that have used it for that, and basically the idea there is it's more to collect, to look at data across multiple consumers and then tell them hey, people like you we think it's better if they eat this type of food, or if we notice that you walk along this way when exercising, but it might be better to go along that way, things like that. Or even just telling you hey, compared to other people, you're in the bottom 40% in terms of I don't know how many stairs you go up or stuff like that. So just to tell you how you compare to others. That's the main thing I've seen.
So let's look at this health company style example as as an example. We can talk about how they might hypothetically build an architecture. So let's say they've got all these consumers that are wearing these health devices, and this data is constantly being sent to the servers at this company. How are they going to build this a Spark system that ingests that data and does useful things with it?
Mm-hmm. So the first thing is to decide where to store the data. So there's several options there. So you can do, for instance, you can just store it in Amazon S3 if you want a cloud service to store it in, which will be very easy. Or if you want an on-premise cluster, you could have a Hadoop cluster, or you could have something like Cassandra, which is more of a it's also good for serving live queries. So that's useful if you want to query the data, to do point queries on it in addition to just storing some logs. So that's the first thing. And then I think most people would begin with some exploratory data science. So then you sit down in front of, say, IPython terminal, or like one of, like a notebook-like interface, like the one that we have in Databricks, where you load in a subset of the data, maybe into memory across the cluster, and then you start slicing it in different dimensions, like trying to answer, say, whatever question or hypothesis you have. Like, for example, if you think, you can like say you can you want to compare each user to other users in their neighborhood and tell them like if they're very different from those in terms of their activity pattern or something like that. So that's like one thing you try to do. Once you that you do it interactively is very similar to using R now. So you type in some commands, you get answers, you type in new ones based on them. And once you come up with something there, like say you want a model of like what which whether this user prefers like one type of activity or another. Once you've built that, the final step is to actually make a kind of a production application, and you could write a streaming application, or you could write a batch one and just like run it every night and maybe email people in the morning or something like that. And hopefully in this case you'd be able to take a lot of the code you wrote during exploration and reuse that code. Just spend some time to harden it, maybe optimize it, or to run it in there.
So when I was listening to that REC podcast, you mentioned something offhand about Spark having BitTorrent built into cluster management. Did I hear you correctly?
So yeah, BitTorrent is not in cluster management, but it is used for some of the communication operations. So like one of the operations is broadcast, where you have a value on like the master node and you need to send it to all the workers, and sometimes these values are really big. Like for example, in machine learning, the value is the parameter vector for your algorithm, and that's something that can be like many, like say 10 million floating point numbers. So that's like a few, like tens of megabytes basically. And we actually use a protocol similar to BitTorrent to send that across all the nodes in the cluster, because you don't want them all just waiting on the master to push that data to them. So yeah.
Do you know of anybody doing interesting things with Bitcoin and Spark?
I've seen a few talks on it, but off the top of my head, I'm not sure. But if you want, I can try to find them. It could be. I think for analyzing the Bitcoin blockchain and like the transactions is probably the best place you try to use it.
The next week of stuff after Big Data Week is going to be Bitcoin Week. So I'll do research on it. Don't worry about it. But I'll be very interested to see how people are using it. So
I'll see if I can find any talk on it.
Interesting. That'd be great. What has changed in the patterns that people use to access big data since the inception of MapReduce?
Yeah. So I think several things changed. So I think first of all, as I mentioned earlier, there's a much wider set of people that want to use this data, because it went from we have this batch job we have to run every night, like say this index of the web, we just want to run this like one application, to we collected lots of data and we have many questions and we want to ask those questions as quickly as possible and expose it to as many users as possible within the organization who might use it to improve, their own products or like whatever they're doing for their job. So that's one thing. Like number of users has increased, and I think also the level of timeliness that people are looking for has increased as well. So both in terms of doing things in a streaming fashion and just answering these interactive queries faster, not having to wait 20 minutes to get back the answer for a query, but getting it back in 20 seconds and moving on to the next one.
What is the future of Spark? Where would you like to see things go?
So I think there's a lot of stuff, still left to do in Spark, and that I think all of us are excited to work on. But I'm really excited to see to see the growth of the standard library and really put together sort of the most comprehensive library for doing data processing in parallel. And I think we already have I think the largest such library that's out there today. But I think there's still a lot of very cool algorithms and functionality, like I mentioned, time series data, geospatial, and so on, that people are figuring out how to do at large scale, and that will be cool to include in there. And then the second thing I'm excited about is the Python and R users, and making this kind of computing infrastructure available to more and more types of users that traditionally would never have touched MapReduce, and it would be too complicated for them to do it. So these are the things I'm excited about. Yeah.
So one of the motifs, I know we're running low on time, so I'll begin to close off, but one of the motifs in this show that I want to build up is this idea that people should be willing to go out and work on their own projects, and if they see a need in the world for a certain technology, they should not be afraid to create it. So, and I think this is essentially what you did with Spark. So do you have any tips or strategies on how to psychologically prepare yourself to write something that is essentially on the front, somewhat revolutionary or somewhat bold?
Yeah, sure. Yeah, so let me mention a couple of things. So the first thing is now with the increasing prevalence of open source software, but also with the really great sort of community tools around it, like GitHub and Docker Hub, the package index for various things like Spark packages or R packages and so on. I think it's easier than ever to create open source software and have other people see it and begin to use it. So all that infrastructure is in there, and it's possible for people to discover it. At the same time, though, if you want people to use it, it's very important to have to start with something that actually solves a need. So, and often the best way to do that is if you have that need yourself, and then obviously that what you're doing is useful, and to also start by making it very small and very simple, so that everyone can understand it and can kind of begin to use it. So, when I look at open source libraries, if there's something, especially if it's something for work where I'm like, oh, should I find an existing library for this, or should we write our own version of this thing? It's always really nice when I look and it's like, oh, it's a pretty small library. It's like 5,000 lines of code or something. I look at it, I can kind of understand it, and I think even if we use this, I'll understand it enough to be able to debug it and to get up to speed quickly. So that's when Spark started out, it was a very small project, and for a long time, a lot of people came in and said okay, well, it's a little bit scary to deploy this totally different distributed computing engine, and if it crashes, my production application is not going to work. But this is small enough that I can understand it, and I'm going to give it a try. So I think this is one of the things that helps Spark and that new projects can do. Sometimes new projects try to do too much at once, and and basically it becomes scary for people to adopt them. So I think these are the things. Make sure it's easy to understand, and make sure people can find it through GitHub or through other sources.
Great, I love that advice. Well, is there anything else you'd like to add?
No, I think that's pretty much it. Yeah, I really enjoyed chatting.
Yeah, Matei Zaharia, thank you so much for coming on Software Engineering Daily. I'm a huge fan of the Spark project, so keep up the good work.